Good morning to all. I am Dr.Dhondiba, Assistant Professor of Chemistry, Government First Grade College, KR from Bangalore. Today I am going to discuss about 8th session of chemistry and 4th session of gaseous state, which belongs to first semester BSc affiliated to Bangalore North University. In this session, I have to discuss about uh, problem solvings on root mean square velocity, average velocity, and most probable velocity. And also, we have to discuss about Andrews isotherms of carbon dioxide. Now, main objectives of these sessions are the solving some problems on most probable velocity, average velocity, and root mean square velocity. Then also we have to determine that is a critical temperature by using a Andrews isotherms of carbon dioxide. Then we have to also discuss in this session as a liquefaction of the gases. This we have to discuss one by one in this session. After completion of this session, you will come to know about the how to solve the problems on most probable velocity, average velocity, and root mean square velocity. Also, you will draw that is a diagram, and everything will be know on Andrews isotherm of carbon dioxide. Then also you have to know about liquefaction of the gases. These we have to know after this completion of this session. Now, before going to discuss this session, you have already know about expressions of most probable velocity, average velocity, and root mean square velocity. Also, you know that that is the critical temperature of the gas, and what is the meaning of liquefaction of the gas. These you have already known. Now coming to that is in this session, what you have to discuss. The first one is you have to we have to solve that is some problems. I will take that is two problems to for solving purpose in this session. The first problem goes to calculate the root mean square velocity, average velocity, and most probable velocity of oxygen molecules at 300 Kelvin. Now solution for this, given that what are the data given here, I have to write here the molecular mass of oxygen molecule. Therefore oxygen molecule is the atomic mass of oxygen is nothing but 16, and two atoms are there, therefore it is became a molecule. Therefore 16 plus 16 it get that is a 32 gram per mole. This is the as a molecular mass of uh, oxygen. Then therefore this gram per mole can be converted into kg per mole by multiplying by 10 raised to minus 3. Okay, therefore molar mass of the oxygen that can be written as m, and this is equal to 32 into 10 raised to minus 3 kg, and this can be after dividing to 32 divided by 1000 means we will get that is 0.032 kg per mole. This is the molar mass of that is a m, it is a represented of that is oxygen, and temperature is given that is a 300 Kelvin. Again you know that real gas constant that is 8.314 joules per Kelvin per mole. Then we have to calculate root mean square velocity, average velocity, and most probable velocity. We know that for root mean, the expression for root mean square velocity, this is equal to square root of 3RT divided by m. Here just in the square root, that is 3 into r is nothing but 8.314 into t is nothing but 300 divided by the m is nothing but molar mass of oxygen. This is equal to 0.032. This is equal to, we will get 483.56 meter per second. This is after taking the square root, we will get that is this value. Again we know that the relationship between root mean square velocity and average velocity, that is a relation. Therefore we can write that is a average velocity is equal to 0.92 into root mean square velocity. For that, after that is a this value we got, no, that you have to substitute in this equation. Therefore this is equal to average velocity is equal to 0.92 into 483.56 meter per second. This is equal to 444.88 meter per second. And again we also know that the most probable velocity and RMS velocity, that is the relation. This is equal to most probable velocity equal to 0.82 into root mean square velocity. This is can be written as 0.82 into 483.56 meter per second, and after multiplying we'll get that is a 396.53 meter per second. This is the value. Therefore we got that is a root mean square velocity, this much value, and average velocity we will get that is a 444.88, and most probable velocity having a that is a 396.53 per meter per second. Now next problem I have to solve, that is second problem. At what temperature will be the average velocity of methane molecules be the same at that of the ethane molecules at 350 Kelvin? Now solution for this question, this problem, the given that molecular mass of methane formula is nothing but CH4, and in the CH4, no, the carbon is one atom, then hydrogens are 4, therefore atomic mass of carbon is nothing but 12 into 1 means 12, and 4 atom of oxygen, therefore 4 into atomic mass of hydrogen is nothing but 1, therefore we will get that is 12 plus 4, therefore it is 16 gram per mole. The molar mass of methane, therefore we can convert that is a gram per mole is into kg per mole, therefore molar mass of methane is equal to m methane equal to 16 into 10 raised to minus 3 kg, and this is equal to 0.016 kg per mole, and this is the molar mass of methane. Similar to that, we have to also calculate that is the temperature, no, we have to calculate the molar mass of molecular mass of ethane also. Before we have to go in, no, before going to this, the temperature of the methane that you have to calculate here, T methane. Then similarly we know that molecular mass of ethane formula is nothing but C2H6 or CH3CH3, means that is C2H6, 2 atoms of the carbon, therefore 2 into 12 plus 6 into atom, that is atomic mass of hydrogen is 1, therefore we will get that is a 24 plus 6, therefore it is a 30 gram per mole, and this will be a convert into molar mass, that is nothing but molar mass of ethane is equal to m ethane, this is equal to 30 into 10 raised to minus 3 kg, this is equal to 0.030 kg per mole. Then temperature of the ethane, no, temperature of the ethane, it will be given that is a 350 Kelvin. Here methane will be given over, but it should be a temperature of the ethane, T ethane is equal to 350 Kelvin. Now we know that the average velocity of methane equal to average velocity of ethane. Therefore you take that is the formula square root of 8RT methane divided by pi m methane. This is equal to the square root of 8RT ethane divided by pi m ethane. Then square cut, that is the square root get cancelled. Therefore we will get that is a 8RT methane divided by pi m methane. This is equal to 8RT ethane divided by pi m ethane. Therefore this 8R the 8R and this 8R get cancelled. This pi get cancelled. Therefore we get that is a T methane. This is equal to T ethane divided by T methane into m methane. You substitute the value of this here. Therefore, T methane equal to 350 Kelvin divided by 0.030 kilojoule, that is a kg per mole, into 0.016 kg per mole. This kg per mole, this kg per mole get cancelled, and after multiplication it will get, that is a T methane is equal to 186.7 Kelvin. This is the temperature. This is the solution for, that is the second problem. Now coming to, that is the liquefaction of the gases. Liquefaction of the gases as a critical phenomena. A gas can be liquefied by lowering the temperature and increasing the pressure. At lower the temperature, the gas molecules lose kinetic energy, because while moving the molecules at the high temperature, the molecules can be moved from one place to other place. When we are removing, that is the temperature, it lower the temperature, the molecules loses the kinetic energy and they comes closer to each other, and it became a liquid, or it convert, that is a one state to other state. Therefore, the and again, that is increasing the high pressure means applying the pressure, the molecules try to comes close to each other. Okay, therefore we say that the slow moving molecules then aggregate due to the attraction between them and are converted into liquid. Therefore we say that as the temperature lowers or decreases and pressure will be increases, the pressure, it all molecules come to close to each other, and temperature lowering the temperature means the kinetic energy will be a loses, and the molecules combine each other and to form a liquid. Therefore gas molecule is converted into liquid. The same effect is observed by increasing pressure. The gas molecules come closer by compression and coils to form a liquid. This is called as a liquefaction of the gases, and it is called as a critical phenomena. Therefore, Andrew studied the pressure temperature conditions of liquefaction of the several gases, and he established that for every gas there is a temperature below which the gas can be liquefied, but above it the gas defies the liquefaction. This temperature is called, that is a critical temperature of the gas. Therefore we can simply define as, at a particular temperature the gas at particular below temperature, at particular below temperature the gas remains in liquid state, and above that temperature the gas cannot be liquefy. Such temperature or that temperature is called, that is the critical temperature of the gas. Therefore we say simply, at particular temperature, the above that temperature the gases remains gaseous state, but liquefy is not possible, and at below that temperature the all gases becomes a liquid and there is no gases will be occurred, and such, that is the temperature is called, that is the critical temperature of the gas. Therefore how do we define, that is the critical temperature means it is represented as, that is the Tc of a gas. It can be defined as the temperature above which it cannot be liquefied. The particular temperature above which the gas cannot be liquefied no matter how great pressure is applied, and such, that is the temperature is called, that is a critical temperature, and it is represented as a Tc. Then coming to, that is a critical pressure. Critical pressure can be represented as Pc, the minimum pressure required to liquefy the gas at critical temperature. At particular critical temperature the minimum pressure is required to get the liquefy the gas, and that pressure is called, that is the critical pressure of the gas. Then critical volume. Critical volume can be represented as Vc. It is defined as volume occupied by a mole of gas at critical temperature and pressure is called, that is the critical volume. Therefore we say that volume occupied by a mole of gas at critical temperature and pressure is called that is a critical volume. Then the critical temperature, critical pressure and critical volume are collectively called as a critical constants of the gas. All real gases have a characteristics critical constant. At critical temperature and critical pressure, the gas becomes identical with its liquid and it is said to be a critical state. Therefore, at particular temperature and pressure, the gas properties identical to the liquid properties, and that state is called as a critical state. The smooth merging of the gas with its liquid is referring to be as a critical phenomena. Andrews demonstrate the critical phenomena in gases by taking the example of carbon dioxide in this session. Therefore, we can explain that is the Andrews isotherms of carbon dioxide. The PV curve, that is the isotherm is nothing but the a series of how it is defined, that is isotherms. Isotherms means a series of graphs or curves are obtained at making the constant temperature. uh, the graph is plotted pressure versus volume. Pressure is taken on that is the y-axis and volume will be taken in the x-axis, and keeping the constant temperature, that particular temperature will get that is series of that is curve or a curve will be get, and that curve is called as isotherm. Therefore, we say that is the pressure volume curves of a gas at constant temperature are called isotherms or isothermals. We can also be defined as such like the series of curves are obtained by uh, different constant temperature by plotting pressure versus volume of a that is a graph, and that is called as a isothermals or isotherms. For an ideal gas, the PV is equal to nRT and the product PV is constant. uh, that is a product when it is a PV is constant means the PV is constant if T is fixed, means here suppose T is making constant, then nRT is the again also constant, therefore whole term is the constant, hence the isotherms would be a rectangular parabolas. Therefore, for ideal gas, the isotherms of the ideal gas is rectangular parabolas. For an ideal gas, PV is equal to nRT and product is constant, it is a fixed, hence isotherms would be a rectangular parabola, we can be say. Okay. Now, then Andrews plotted the isotherms of carbon dioxide for a series of temperature. From the figure, we can see that there are three types of the isotherms. That is which because that is those above the 31 degrees Celsius and those below the 31 degrees Celsius and at the 31 degrees Celsius. Therefore, we say that is a three types of the series of the curves of that is carbon dioxide obtained. 31 degree above the curves are there and below the curves are there, and at the 31 degree the curves will be there, that we have to study. At that is isotherms above the 31 degrees Celsius, the temperature no here in this series no, here pressure in atmosphere and here volume no, then here the series of curves will be there. At ideal gases no, that is it becomes a rectangular parabola. Okay, rectangular parabola, it is ideal, but it is real gases that deviates from that is ideal gas equation or ideal graph, therefore it deviates. Okay, therefore as carbon dioxide we are taking from that is a 48 degrees Celsius, it is due that is this like, again we are lowering the temperature 35, this will be bends again 30, it will be get, it becomes a liquid here. Therefore this can be say that is a here this portion green portion we say that is a here it is a liquefied, and above this is the gaseous state. Okay, therefore we can say that is the F portion at this portion is nothing but that is a critical point and it is called as a 31 degrees Celsius, it is a critical temperature. Therefore, at above 31 degrees Celsius, the isotherms at 48 or 49 degrees Celsius, it is a rectangular hyperbola, and approximate to isotherms of ideal gas. It is exactly at 49 degrees Celsius or 48 degrees Celsius. It is a rectangular hyperbola, and it is considered as a ideal gas because is ideal gas having a rectangular parabola, no, like that this will be a form. So are all other isotherms of above 31 degrees Celsius. Thus, in the region above the isotherms of 31 degrees Celsius, carbon dioxide always exists in the gaseous state. Why? The carbon dioxide remains gaseous state above the 31 degrees Celsius means it is just like a ideal that is ideal gas or rectangular parabola it forms, and therefore it is gives that is always that is a gaseous state. Then second B is nothing but isotherms below 31 degrees Celsius. The isotherms below 31 degrees Celsius are discontinuous, means it is not a constant but it is changing rapidly or different portion. For example, the isotherms of 21 degrees Celsius consist of three parts. Considering that is at 21 degrees Celsius, these are the three parts will be there. How it is to explain? At one first curve is curve AB. It is the PV curve for the gaseous carbon dioxide. Along AB, the volume decreases gradually with the increase in pressure. Here we know that here the volume AB, no, it is the decreases of the gases gradually, and it is suddenly it is liquefied and it is remains constant. That can be explaining here. Therefore, we say that is a PV curve of the gaseous carbon dioxide. Along AB, the volume decreases gradually with increase of pressure. At B point, the volume decreases suddenly due to the formation of liquid carbon dioxide having a higher density. That can be here. You see that is this is the gradually decreases and it is suddenly decreases and it converts into a liquid state at this pressure. The pressure will be remains constant but it becomes a liquid, and due to the high density of that gas molecules. Then the horizontal portion of that is a BC. Along the horizontal part of BC of a isotherms, the liquefaction process continues while the pressure is held constant. At C point or C, all the gas is converted into liquid. What is that BC portion? You see here in this BC portion, BC AB, then it is a BC portion. No, this is the BC portion. It is a continuous, discontinuous, and it remains constant. Okay. Therefore, we say that is below that BC is a horizontal, and that is a liquefaction continuous while the pressure is held constant. At C, all the gases is converted into liquid state. Then the vertical CD. This part of the isotherms is in fact PV curve, liquid carbon dioxide. This is almost vertical since liquid is not very compressible. Here we say that is it is in this form it is vertically it takes place, and it is remains actually this is the gaseous state, and after that is not compressible. It is not a compressible liquid. It cannot be compressed. The gases are it is certain compressible, but it is further it is not compressible and it remains in the gaseous state. It cannot be liquid state. Therefore, BC is a vertical line. Okay. Now coming to that is another one, that is isotherms at 31 degrees Celsius. Andrews noted that above 31 degrees Celsius there was no possibility of liquefaction of the carbon dioxide. However, great the pressure is applied. The pressure is applied so much, but there is no liquefaction is possible above the 31 degrees Celsius, and therefore it is called as a critical temperature. The critical temperature of the carbon dioxide, therefore 31 degrees Celsius. The isotherms EFG at this temperature is called that is a critical isotherms. EFG, this is the isotherm Isotherm is, that is a EFG. This is the EFG. That is the curve will be, that is a dark red line will be there. That is curve. This is isotherm because temperature is keeping constant at 31 degree, and we are studying the how it is the volume and pressure changes at this temperature. That can be explaining. That is called as isotherms. Now here, therefore, the isotherm EFG at this temperature is constant, is called, that is a critical isotherms. The EF portion of critical isotherms represents the pressure volume curve of the carbon dioxide. At the point F, the curve records a twist which is coincided with the appearance of liquid carbon dioxide. Here the gas and liquid have the same density and indistinguishable. Here what happened here, this is the at particular temperature, that is the F point now. Here we say that is a, here in the graph at F, here that is sharp, here both properties are there. The gas and that is the liquid cannot be distinguishable. It is a cannot be distinguished. It is a same property, that is a both property will be there. The gas having a liquid property, liquid having a gas also property. Therefore we cannot be judge whether it is a liquid or gases at this F point. The due to having a same density, then the point is called, that is that point, that is F point is called as a critical point and nearly parallel to the vertical axis and marks as a boundary between the gaseous carbon dioxide on the right and the liquid carbon dioxide on the left. Here therefore we say that is a, here mark no, this is on, that is the left side, this is right side, that is gases, and this side it is a liquid state. Here will be the marked, this is the F, it is called as a critical point, and 31 degrees Celsius is a critical temperature. Therefore so far we have to discuss about we have to solve the problems on, that is the most probable velocity, then average velocity, then also on the that is the root mean square velocity. Then we have already explained or known about, that is the liquefaction of the gas. What is the liquefaction will be takes place, and what is the meaning of liquefaction I have explained. Again critical constant, that is a PC, TC and VC, that is a critical constant, no, critical temperature, critical pressure, critical volume, you have already known. Then also you have already known about, that is we have discussed in this session anti isotherms of carbon dioxide. These we have discussed. So that I will ask some questions. You have to think carefully and you have to answer the correct answer for that question. The first question goes to, that is a temperature above which gas cannot be liquefied no matter how great pressure is applied. Then what is that? What temperature? That is what is called, the option will be given: A option normal temperature, B option critical temperature, C option critical volume, and D option critical pressure. Now I will give just 10 seconds for you people. You have to answer the or choose the correct option for this question. The option for this question is the critical temperature. The critical temperature is the definition of this is where the temperature above which the gas cannot be liquefied no matter how great pressure is applied is called, that is a critical temperature. Therefore B option is the right option or right answer for this question. Then second question, the minimum pressure required to liquefy the gas at critical temperature. The first option goes to normal pressure, second option goes to critical temperature, the third option goes to critical volume, and D option goes to critical pressure. I will give just 10 seconds for you people. You have to select correct options. Answer for this question is, that is the critical pressure, means that is the D option is the right option. The minimum pressure required to liquefy the gas at critical temperature is called as a critical pressure. The D option is the right option for the this question. Then third question goes to the volume occupied by a mole of gas at critical temperature and pressure is called, what is that? Normal volume, critical temperature, critical volume, critical pressure. I have to give just 10 seconds for you people. You have to choose the correct answer. The answer for this is C option. Critical volume is the right option for this question. Therefore, the critical volume is defined as the volume occupied by a mole of gas at critical temperature and critical pressure. Card, that is a critical volume. Therefore, C option is the right option for this question. Then fourth one, isotherm of ideal gas is, isotherms of ideal gas is, first option rectangular parabola, B simple parabola, C ellipse, and D is nothing but none of these. I will give just 10 seconds for you people. You have to select right option. A option is the right option for this question because the isotherms of ideal gas is always a rectangular parabola. Therefore, A option is the right option. Then fifth question is, critical temperature of the carbon dioxide is, critical temperature of a carbon dioxide is at 48 degrees Celsius, 31 degrees Celsius, 21 degrees Celsius, and D is nothing but none of these. I will give just 10 seconds for you people. You have to choose the correct answer. B option of this question is right option because the critical temperature of the carbon dioxide is 31 degrees Celsius. And so for preparation of this session, no, I refer these books and this complete, that is session number 8. Thank you.